Welcome to the Nocturnal Astronomer, a channel built for quiet nights, wandering minds, and anyone who finds the universe to be the perfect companion for sleep and relaxation. Whether you are drifting off, unwinding after a long day, or simply looking for something calming to fill the background, you are in the right place. I am Atlas Reid, your host on these slow journeys through the cosmos. Tonight, we are going somewhere extraordinary. We are going to the coldest places the universe has to offer. Places so impossibly frigid, they make the darkest winter night feel like a warm afternoon. Let's dive in. Part 1. What cold really means. Temperature is not simply a feeling. It is a measurement of how much energy the tiny particles inside any given substance are holding on to. When a substance is warm, its particles are moving quickly, bouncing and vibrating with enthusiasm. When something is cold, those particles slow down considerably. The coldest possible temperature, the point at which particle motion theoretically stops entirely, is known as absolute zero. It sits at minus 273 degrees Celsius or minus 459 degrees Fahrenheit. Nothing in the known universe has ever been measured at exactly this temperature. Scientists use a scale called the Kelvin scale when discussing temperatures in space. On this scale, absolute zero is simply 0 Kelvin. The freezing point of water sits at 273 Kelvin, and room temperature hovers around 293 Kelvin. When we talk about cold places in the universe, we are often talking about temperatures just a few degrees above absolute zero, or sometimes fractions of a single degree above it. To put that in perspective, the difference between those temperatures and absolute zero is smaller than the difference between a warm cup of tea cooling by a single degree. The universe began extraordinarily hot. In the first moments after the Big Bang, temperatures were so extreme they are nearly impossible to describe in everyday terms. Everything since then has been a long, slow cooling, a gradual release of energy spreading outward across billions of years. Today, the average temperature of space itself, the background radiation left over from the Big Bang, sits at about 2.7 Kelvin. That is just 2.7 degrees above absolute zero. Space is already extraordinarily cold, but some places manage to go even further into the chill. Cold in the universe is not evenly spread. Stars and galaxies generate enormous heat, but the spaces between them and the quiet corners tucked away from any source of energy can reach temperatures that challenge the very boundaries of what we understand about matter. Understanding cold also means understanding stillness. The closer something gets to absolute zero, the more its internal activity grinds to a halt. Atoms become sluggish, reactions slow. In the coldest places in the universe, time itself seems to take a long, slow breath. These are the places we are visiting tonight, not the blazing hearts of stars or the violent collisions of galaxies, but the quiet, still, impossibly cold corners of the cosmos, where the universe has been exhaling for billions of years without interruption. Part 2. The Cosmic Microwave Background. After the Big Bang, the universe was a dense, glowing fog of energy and matter. Light could not travel freely through it. Everything was too tightly packed, too hot, too chaotic for photons to move more than a short distance before being absorbed again. About 380,000 years after the Big Bang, something changed. The universe had expanded and cooled enough that electrons and protons could finally combine to form neutral hydrogen atoms. This moment, called recombination, allowed light to travel freely for the first time. That ancient light is still traveling today. It has been stretched by the expansion of the universe across nearly 14 billion years of cosmic history. By the time it reaches us, it has been stretched so far that it no longer appears as visible light at all. It has become microwave radiation. This ancient glow is called the cosmic microwave background. It fills the entire sky in every direction. It is one of the most uniform things in the observable universe, a nearly perfect bath of radiation left over from the earliest moments of existence. The temperature of the cosmic microwave background today is approximately 2.7 Kelvin. That number might seem almost warm compared to some of the places we will visit tonight, but consider what it represents. It is the temperature of the entire observable universe, averaged across everything we can see. Think of the cosmic microwave background like the last warmth left in a room long after the fire has gone out. The fire was the Big Bang, the warmth still faintly lingering in the walls and the floor and the air is the background radiation we measure today. Within the cosmic microwave background, there are tiny fluctuations. Some regions are slightly warmer, some slightly cooler. The differences are extraordinarily small, fractions of 1/1000th of a degree. But these tiny variations were the seeds of everything. Galaxies, stars, and planets all grew from these faint ripples. The coolest patches of the cosmic microwave background sit just fractions below the average temperature. They represent regions of the early universe that were slightly less dense, slightly less energetic. Over billions of years, those regions became the vast, quiet voids between galaxy clusters. The cosmic microwave background is our oldest photograph of the universe. It is also, in a sense, a temperature map of creation itself, a record of where cold and warmth began to diverge in the very first chapters of cosmic history. Part 3. The Boomerang Nebula. If the cosmic microwave background represents the average cold of the universe, then the Boomerang Nebula represents something even more remarkable. It is a cloud of gas and dust located about 5,000 light-years from Earth, and it is the coldest naturally occurring place ever discovered in the universe. The Boomerang Nebula was formed by a dying star, shedding its outer layers at extraordinary speed. At the center of the nebula sits what remains of the original star, a dense stellar remnant pouring energy outward into the surrounding cloud of ejected material. The gas in the Boomerang Nebula is expanding outward at roughly 164 kilometers per second. That is fast enough to travel from one side of Earth to the other in less than a single minute. This rapid expansion is the key to understanding why the nebula is so cold. When a gas expands rapidly, it cools. This is the same principle at work when you spray air from a compressed can and the nozzle feels cold to the touch. The gas inside is under pressure. When it escapes and expands, its temperature drops dramatically. In the Boomerang Nebula, this process has been happening on a cosmic scale for thousands of years. The gas has expanded so far and so fast that it has cooled to just 1 Kelvin, 1 degree above absolute zero. That makes it colder than the cosmic microwave background itself. That is a remarkable fact worth sitting with for a moment. The leftover glow of the Big Bang, spread across the entire observable universe, is warmer than this single cloud of gas drifting quietly through our galaxy. The Boomerang Nebula is, in the truest sense, colder than space itself. The nebula gets its name from its shape, which early observations suggested resembled a boomerang. Later, higher resolution images revealed a more complex, almost hourglass form, with 2 lobes of gas spreading outward from the central star in opposite directions. The Boomerang Nebula is not expected to remain this cold forever. As the expansion slows over thousands of years, the gas will gradually warm, absorbing energy from the surrounding universe. For now, though, it holds the title of the coldest known place that nature has created on its own. It is a quiet monument to the power of expansion, a reminder that cold is not just the absence of heat, but the result of a process, a story written in the slow outward drift of stellar material across thousands of years of cosmic time. Part 4. Cold inside molecular clouds. Scattered throughout galaxies like our own Milky Way are enormous collections of gas and dust called molecular clouds. These are not the wispy, decorative nebulae often shown in telescope images. They are dense, dark, cold regions where the building blocks of stars slowly gather over millions of years. Molecular clouds are called molecular because within them, hydrogen exists not as single atoms, but as paired molecules, two hydrogen atoms bonded together. This happens because the clouds are shielded from the radiation of nearby stars, allowing chemistry to take place at extremely low temperatures. The temperatures inside molecular clouds typically range from about 10 to 30 Kelvin. That is still extraordinarily cold by any everyday standard. At 10 Kelvin, the particles inside the cloud are moving so slowly that complex molecules can form and remain stable without being torn apart by heat. These clouds are also remarkably dense by the standards of interstellar space, though they would still count as a near-perfect vacuum by any laboratory measure on Earth. Within their densest regions, called dense cores, the temperatures drop even further, and the material becomes thick enough to begin collapsing under its own gravity. It is inside molecular clouds that stars are born. As a dense core collapses, it heats up. Gravity pulls material inward, and as that material compresses, it converts gravitational energy into heat. Eventually, the core becomes hot enough to ignite nuclear fusion, and a new star is born. Think of a molecular cloud as a slow, cold nursery. The temperatures are low, the activity is minimal, but within that stillness, something is always quietly gathering, always slowly building toward the moment when enough material has come together to light a new fire in the sky. Some of the most famous molecular clouds visible from Earth include the great clouds in the constellation Orion. Within those clouds, new stars are forming right now, hidden behind curtains of cold dust that block visible light but glow in infrared wavelengths. The cold interior of a molecular cloud also allows for the formation of complex organic molecules. Scientists have detected hundreds of different molecular species inside these clouds, including some of the basic chemical building blocks associated with life. Cold, it turns out, is not the enemy of chemistry. In some cases, it is the condition that makes chemistry possible. Molecular clouds are among the most important structures in any galaxy. They are cold, quiet, and patient. They are also where the universe does some of its most meaningful work, slowly assembling the ingredients for new stars, new planets, and perhaps new beginnings. Part 5. The Cold Hearts of Dark Nebulae. Within molecular clouds, the coldest and densest regions are known as dark nebulae. These are pockets of gas and dust so thick that they block almost all of the light from stars behind them. When you look at a photograph of a star field with an unusual dark patch in the middle, you are often looking at a dark nebula. Dark nebulae were once thought to be simply empty regions of space, gaps in the distribution of stars. It was only with more careful observation that astronomers realized these dark patches were not empty at all. They were filled with material, just material so dense and cold that it absorbed rather than emitted light. The temperatures inside the coldest dark nebulae can drop as low as 7 or 8 Kelvin. That is not quite as cold as the Boomerang Nebula, but it is still extraordinarily frigid, cold enough that even simple chemical reactions slow to a near halt, and molecules remain frozen in place for millions of years. One of the most studied dark nebulae is called the Barnard 68 cloud, though it is better known simply by its nickname, the Dark Globule. It sits about 500 light-years from Earth and appears as a near-perfect circle of darkness against a background of stars. It is small by cosmic standards, about half a light-year across. Inside such globules, the conditions are almost perfectly still. There is no radiation from nearby stars to stir the gas. There are no shock waves from supernova explosions to send ripples through the material. Just cold, quiet, slowly settling dust and molecules drifting in the dark. Eventually, even these still dark cores will collapse. Gravity is patient. Over millions of years, the material at the center of a dark nebula will gather enough mass to begin a slow inward fall. The cold core will warm. The dust will clear. A new star will ignite in what was once a patch of perfect darkness. There is something almost meditative about dark nebulae. They exist in a state of suspended quiet, not yet stars, not yet anything recognizable, just potential energy waiting in the cold. They are the universe holding its breath before something new begins. The dust grains inside dark nebulae are coated in thin layers of ice. Water ice, carbon dioxide ice, and other frozen compounds cling to the surfaces of tiny particles, forming a kind of frozen chemistry set that will eventually be incorporated into new planetary systems. Dark nebulae are, in their way, some of the most consequential places in the galaxy. Their cold interiors are where the raw materials of future worlds are stored, frozen and waiting until gravity finally calls them inward, and the long process of star and planet formation begins again. Part 6. Neutron stars and surface cold. Neutron stars are among the strangest objects in the universe. They are the collapsed remnants of massive stars that ended their lives in supernova explosions. What remains after such an explosion is that a single teaspoon of its material would weigh billions of tons on Earth. Newly formed neutron stars are extraordinarily hot. In the immediate aftermath of a supernova, their surfaces can reach temperatures of hundreds of billions of Kelvin. They radiate energy furiously, glowing across the entire electromagnetic spectrum in the moments after their formation. But neutron stars cool over time. Without an ongoing source of nuclear fuel, they gradually radiate away their heat into the surrounding space. Over millions of years, a neutron star's surface temperature drops from its initial extreme heat towards something much quieter. Older neutron stars, those that formed billions of years ago and have had time to cool, can have surface temperatures of just a few 100,000 Kelvin. That still sounds extremely hot, but compared to a newborn neutron star, it represents a dramatic cooling. In cosmic terms, an old neutron star is a fading ember. Some of the coldest known neutron stars have surface temperatures that have dropped to around 50,000 Kelvin or below. Their interiors may be even colder, though the extreme densities involved make the physics of neutron star interiors one of the most challenging problems in modern astrophysics. There is a layer inside a neutron star where the matter may exist in a state unlike anything found anywhere else in the universe. At the extreme densities of a neutron star core, protons and electrons are crushed together into neutrons, and those neutrons are packed so tightly that they may behave as a kind of frictionless fluid. This state of matter, called a neutron superfluid, has never been directly observed, but the way certain neutron stars occasionally glitch, suddenly spinning slightly faster before slowing again, is consistent with what we would expect if a superfluid layer existed deep inside them. Cold neutron stars are also quiet neutron stars. Young neutron stars spin rapidly and emit powerful beams of radiation. As they age and cool, they slow down. The oldest, coolest neutron stars are often nearly undetectable, dark and still against the background of space. A cold neutron star drifting through the galaxy is one of the lonelier images the universe offers. It was once the blazing heart of a massive star. It survived one of the most violent events in all of nature, and now it drifts quietly, cooling degree by degree, growing darker with each passing million years. Part 7. White Dwarfs Growing Cold. White dwarfs are the cooling remnants of stars like our own Sun. When a Sun-like star exhausts its nuclear fuel, it swells into a red giant and then sheds its outer layers, leaving behind a small, dense core made primarily of carbon and oxygen. This core is the white dwarf. White dwarfs are not powered by nuclear fusion. They have no fuel left to burn. Instead, they simply radiate away the heat stored inside them, slowly cooling over billions of years, like a brick pulled from a furnace and left to sit on a cold floor. A newly formed white dwarf can have a surface temperature of over 100,000 Kelvin. It is extremely luminous for its size, glowing intensely in ultraviolet light. But without any energy source to replenish what it radiates away, the cooling is steady and inevitable. Over billions of years, a white dwarf fades. Its surface temperature drops from 100,000 Kelvin to 50,000, then to 20,000, then to 10,000. Our own sun, when it eventually becomes a white dwarf, will follow this same long, slow path into the cold. The coolest white dwarfs discovered so far have surface temperatures of around 3,000 to 4,000 Kelvin, which puts them in roughly the same temperature range as the cooler class of red dwarf stars. At this temperature, they glow a deep, dim red, rather than the brilliant white of their younger counterparts. In theory, a white dwarf that has been cooling for long enough will eventually drop below any temperature we would associate with visible light. It would become a black dwarf, an inert, cold ball of crystallized carbon and oxygen, drifting invisibly through space. Here is an important detail, though. The universe is only about 13.8 billion years old. White dwarfs cool very slowly. No white dwarf has had enough time to cool all the way to black dwarf status yet. Black dwarfs are a prediction, not yet an observation. They belong to the far future. The coolest white dwarfs we can currently observe are among the oldest stars in the galaxy. They formed early in the Milky Way's history, burned through their fuel, shed their outer layers, and have been quietly cooling ever since. They are dim, ancient, and extraordinarily faint. Finding these cool white dwarfs is one way astronomers measure the age of the galaxy. By looking at how cold the coolest white dwarfs have become, and knowing how long the cooling process takes, scientists can estimate how long ago the first generation of stars in our galaxy began to form. Part 8. Voids between galaxy clusters. Between the great clusters and filaments of galaxies lies some of the emptiest space in the observable universe. These regions, called cosmic voids, are not completely empty. They contain a thin scattering of gas, a handful of galaxies, and very little else. They are also extraordinarily cold. The gas that fills cosmic voids is so thin that it barely interacts with anything. There are no nearby stars to heat it. There are no dense clouds to trap radiation. The gas simply drifts in near isolation, cooling slowly as the universe around it continues to expand. Temperatures in the most underdense regions of cosmic voids can drop close to the temperature of the cosmic microwave background itself, around 2.7 Kelvin, there is simply not enough energy input from any source to raise the temperature significantly above the ambient background level. Cosmic voids are enormous. Some of the largest known voids stretch for hundreds of millions of light years in every direction. If you were somehow placed at the center of one, the nearest galaxy might be tens of millions of light years away in any direction. The sky would be almost completely dark. These vast, empty regions are not simply spaces where matter forgot to show up. They are the result of gravity pulling matter outward and away from certain regions over billions of years. The denser regions attracted more material, leaving the voids increasingly empty as time passed. Think of cosmic voids like the holes in a piece of Swiss cheese. The cheese itself, dense with matter, represents the filaments and clusters of galaxies. The holes represent the voids, regions that have been progressively emptied as the surrounding structure grew denser and more organized. Within cosmic voids, time feels different in a conceptual sense. There are no stars being born or dying nearby. There are no supernovae lighting up the surrounding space. The thin gas inside a void drifts almost unchanged across hundreds of millions of years, quietly cooling in the dark. Some smaller, quieter galaxies do exist within cosmic voids. They tend to be simpler in structure than galaxies found in dense clusters, shaped less by gravitational interactions with neighbors and more by their own internal processes. They are solitary, independent, and unhurried. Cosmic voids are the universe at its most expansive and its most still. They are the cold, empty lungs of the cosmic web, the spaces between everything that give structure and definition to all that surrounds them. Part 9. The Future of Cold. The universe today is about 13.8 billion years old. It is still relatively young in the context of the timescales involved in its ultimate fate. In the far future, the universe will continue to expand, cool, and change in ways that make the cold places of today seem almost warm by comparison. Stars are forming at a lower rate today than they were several billion years ago. The supply of gas available to form new stars is slowly being used up. Eventually, star formation will slow further and then stop almost entirely, leaving only the stars that already exist to gradually burn through their remaining fuel. As existing stars age and die over the next few trillion years, the galaxy will grow dimmer. Red dwarf stars, the smallest and coolest class of stars, will be the last to fade. They burn their fuel so slowly that some will remain shining for 10 trillion years or more before finally cooling into darkness. When the last stars have gone out, the universe will enter a period through a process called Hawking radiation. The temperature of the universe during the degenerate era will drop far below anything we experience today. As the cosmic microwave background continues to cool with the expansion of the universe, the background temperature of space will fall from 2.7 Kelvin toward values that approach but never quite reach absolute zero. Eventually, over timescales so vast they challenge comprehension, even black holes will evaporate. The last black hole to disappear will release a final faint burst of radiation, and then the universe will contain almost nothing but a thin scattering of elementary particles drifting in near total darkness. This final state, sometimes called the heat death or the big freeze, is not hot at all, despite its name. It is the ultimate cold, a state of maximum entropy in which no energy can flow from one place to another, because everything is at the same extraordinarily low temperature. Nothing moves, nothing changes. The universe simply is. It is a profound and quietly unsettling thought, but it is also extraordinarily distant. The timescales involved are so incomprehensibly large that every human civilization, every star that has ever shone, every galaxy that has ever formed, all of it occupies only the very first fraction of a fraction of the universe's full lifespan. For now, the universe is still young, still active, still warm enough in enough places for stars and planets and curious minds to exist. The cold future is a long way off. Tonight, there is still light enough to wonder by. Part 10: Human-Made Cold and Cosmic Context. While nature produces cold through expansion, isolation, and the slow passage of time, humans have also learned to create extraordinarily low temperatures in laboratories. The coldest temperatures ever achieved on Earth were produced not by any natural process, but by physicists studying the strange behavior of matter near absolute zero. In laboratory settings, scientists have cooled small samples of matter to temperatures within a billionth of a degree of absolute zero. These achievements require enormous precision, sophisticated equipment, and conditions that can only be maintained for fractions of a second before warming inevitably occurs. The techniques used to reach these temperatures involve trapping atoms using lasers and magnetic fields, then carefully removing energy from the system in tiny increments. The process is painstaking and delicate. A single vibration from outside the experiment can introduce enough energy to warm the sample and ruin the measurement. At temperatures this close to absolute zero, matter begins to behave in ways that seem to defy everyday intuition. Certain materials become superconductors, conducting electricity with absolutely no resistance. Others form a state called a Bose-Einstein condensate, in which a group of atoms essentially merges into a single quantum entity. A Bose-Einstein condensate behaves like a single giant atom. All the individual atoms within it lose their independent identities and begin to act in perfect unison. It is one of the most exotic states of matter known to science, and it only exists within a tiny fraction of a degree above absolute zero. The coldest temperature ever produced in a laboratory, achieved by researchers working with ultra-cold atomic gases, sits at around 38 trillionths of a Kelvin above absolute zero. Written as a decimal, that number has 11 zeros between the decimal point and the first significant digit. To put that in context, the Boomerang Nebula, the coldest known natural place in the universe, sits at 1 Kelvin. Laboratory cold goes roughly 26 billion times colder than that. In the pursuit of absolute zero, human ingenuity has actually surpassed what the universe manages on its own. This is not a small achievement. The universe has had nearly 14 billion years and the full range of cosmic processes at its disposal. A handful of physicists in a carefully controlled room managed to produce something colder than anything nature has yet created at full scale. The study of ultra-cold matter has practical applications beyond pure physics. Advances in superconductivity, quantum computing, and precision measurement all draw on what researchers learn from working at temperatures near absolute zero. The coldest places in human experience are quietly shaping some of the most important technologies of the coming century. Part 11. Ice in the Solar System. Cold does not only exist in the deep reaches of intergalactic space or the interiors of dying stars. It is also present in our own solar system, sometimes in places surprisingly close to the warmth of the sun. Ice and cold survive in the solar system by hiding from direct sunlight, or by existing so far from the sun that its warmth barely reaches them. The permanently shadowed craters near the poles of the Moon contain some of the coldest surfaces in the solar system. Inside these craters, sunlight never reaches the floor. Temperatures in the deepest shadowed regions can drop to around 40 Kelvin, making them colder than many surfaces in the outer solar system. Water ice has been confirmed in these lunar polar craters. It likely arrived over billions of years, delivered by comets and asteroids that struck the Moon. Because the crater floors never see sunlight, the ice has remained frozen and relatively undisturbed for potentially billions of years. Mercury, the planet closest to the Sun, also harbours ice in its polar craters for the same reason. Despite surface temperatures on Mercury's sunlit side reaching over 400 degrees Celsius, the permanently shadowed polar regions are cold enough to preserve water ice indefinitely. Proximity to the Sun is no guarantee of warmth everywhere. The outer solar system is a realm of deep cold. Jupiter's moon Europa, which sits more than 700 million kilometers from the Sun, has a surface covered in water ice. Beneath that ice, a global ocean of liquid water may exist, kept warm by tidal heating from Jupiter's gravity rather than sunlight. Pluto, orbiting at an average distance of nearly 6 billion kilometers from the Sun, has a surface temperature of around 40 Kelvin. Its thin atmosphere partially collapses and freezes onto the surface during the coldest parts of its long elliptical year, then slowly thaws and returns to gas as Pluto swings slightly closer to the Sun. Even further out, in the region beyond Neptune, where comets originate, temperatures drop toward the background level of space itself. The icy bodies drifting there, some of them preserved nearly unchanged since the formation of the solar system 4.5 billion years ago, represent a kind of frozen archive of the early solar system's chemistry. Comets that occasionally fall inward toward the Sun carry material from this cold outer reservoir. As they approach the Sun, the ice sublimates directly from solid to gas, forming the glowing tails that have been observed and recorded by humans for thousands of years. Each comet is a small piece of the cold outer solar system, briefly made visible by heat. The solar system, taken as a whole, is a story of cold and warmth in constant negotiation. The Sun dominates near its center, but cold persists in shadows, at distances, and in the quiet, icy reservoirs of the outer reaches, where the Sun's influence finally gives way to the ambient chill of interstellar space. Part 12. Sitting with the Cold. Cold, as we have travelled through it tonight, is not simply an absence. It is not just the lack of heat. It is a condition with its own properties, its own chemistry, its own beauty. It is where the universe stores its most patient processes, its oldest light, its most ancient ice. The Boomerang Nebula drifts through our galaxy at 1 Kelvin, colder than the leftover glow of creation itself. Molecular clouds collapse slowly in the cold over millions of years, building new stars from stillness. Dark nebulae hold frozen chemistry, waiting for the warmth of a new sun to unlock it. White dwarfs cool toward eventual darkness over timescales that dwarf the current age of the universe. Neutron stars drift and fade. Cosmic voids stretch across hundreds of millions of light years, filled with gas so thin and cold that it barely registers as anything at all. In laboratories on Earth, physicists have pushed matter to temperatures the universe has not yet managed at natural scale. They have found strange and beautiful states of matter, waiting just above absolute zero, states that have never existed anywhere in the cosmos outside of carefully controlled experimental chambers. And in the far future, cold will win. Not violently, but slowly, steadily, over timescales so vast they resist meaningful description. The universe will cool toward its final state, a stillness so complete that nothing distinguishes one moment from the next. But that future is unimaginably distant, and in the meantime, there is so much warmth. There are stars being born in cold molecular clouds right now, heating the dust around them into glowing shells of colour. There are planets with ice-covered oceans kept liquid by tidal forces and internal heat. There are comets falling sunward from cold reservoirs, blazing briefly as they go. The cold places of the universe are not empty or lifeless in any final sense. They are the quiet places, the waiting places. They are where the universe rests between one act and the next. They are the deep breath before the next star ignites. There is something calming in that, something worth carrying with you into the night. The universe is vast and cold and patient, and within that patience, extraordinary things are always slowly becoming. Cold is not the end of the story, it is the silence between the chapters. And wherever you are tonight, whatever warmth surrounds you, you exist in a remarkably narrow band between the heat of stars and the cold of space. That is not nothing. That is, in the context of everything we have explored tonight, something close to miraculous. And on that note, we come to the end of tonight's journey through the coldest places the universe has to offer. From the background radiation of creation to the frozen shadows of polar craters, from dying stars cooling toward darkness to the impossible chill of laboratory experiments, cold is one of the universe's most patient and persistent forces. Thank you for spending this time with the Nocturnal Astronomer. Whether you are still awake or drifting off somewhere warm, I hope the universe feels a little more familiar tonight. Until next time.